Hello, what we're going to do today is we're going to talk about 1B. 1B is going to talk about distances in space. First thing we're going to do is we're going to talk about distance between the Earth and everything out there. First thing is going to be the moon, and if we looked at a scale version of the Earth-Moon distance, we'll see it's there. And if we notice here that we've got some things that are out of scale, the Earth really is not this big compared to the moon. The moon is about 1/6 the size, so it takes about six moons to go across in every direction. So if we take a look at it, we'll find out that the moon is 200 and about 40,000 miles away from the Earth. And if we talk about distances, these are huge numbers. There's the distance in kilometers, 3,804,000 kilometers. But we can actually use quicker things to actually show this distance. And this time we'll talk about light seconds. Light travels at 186,000 miles per second. So if you take a look at this number right here, it actually takes 1.28 seconds for a message traveling at the speed of light, like a radio message or light, to travel from the Earth all the way to the moon. And then another 1.28 seconds to come back. So if you're on the Earth talking to somebody on the moon, and if you ever seen some of the videos of Earth talking to the moon, the astronauts that are on the moon, the Apollo astronauts, it's almost like, and if you look at sports things, the United States here, we're located about right here. If we're talking to something over here in Europe or over here in Asia or down here in South America, it's almost like when they send a message out, like a question, the person stands there with a blank face and then finally responds. Well, it's because it takes the message a little while for it to get there. So, one light second, 186,000 miles, and another 0.28 seconds to get all the way to the moon. I don't know if you can see the moon because I think my face is right there. Okay, the solar system. We're going to talk about distances now in AUs. AU is a distance, and actually I want to show you this. Scale, usually it's only one is correct, and the distances are not correct here, but the sizes are. Sun is 108 Earths to go around. Jupiter is much bigger than the Earth. There's the distance between the Earth and the Moon, which is not in scale. The scale between the things are not in scale, and I'll show you that in a second. But the first thing I want to do is I want to show you about the scale between what's called an AU. So I'm going to click here. It's going to open up a website. And if you take a look at it, this doesn't show very well. But if I go all the way over, I think you can see at least part of this sun. And to actually get to the Earth, we have to scroll all the way across. And you can see my scroll bar down here, at the bottom, all the way over. And you're not going to be able to see the Earth and the Moon because it's cut off. But basically, if you take a look at it, we've got the sun on this end, which you can't see, and we have the Earth way the heck over here on this other side of the screen, which again, you can't see. That didn't show very well. I'll have to show that in class. Okay, so this is an AU. It's called an astronomical unit, and I'm going to want you to write these things down. An astronomical unit is a distance of 150 million kilometers, 93 million miles, and is the distance between the sun and the Earth, and we know this distance very, very, very well. It takes 500 light seconds for light to get from the sun to the Earth, and that works out to about 8.32 light minutes, so about 8 1/3, actually about 8.5 minutes to make it all the way to the Earth. So there's our little draw diagram. What I do want you to do is I want you to put a sun here. I want you to put Mercury here and say that that is 0.39 AUs. And that means it's about 40% the distance between the Earth and the sun. So it's about 40% of the distance. Venus is also inside the Earth, so it's going to be a number less than 1. It's 0.72 AUs. The Earth, 1.0 AUs. Mars is 1.5 times as far out. The asteroid belt is actually 2.2 to 3.2 AUs, so it's 2.2 to 3.2, and basically it's an AU wide. Ceres, which is down here, this is one of the biggest. It's 600 miles across. It's one of the biggest asteroids. It's actually a minor planet, same as this little guy way over here. 2.8 AUs, so it actually puts it somewhere in the middle of this asteroid belt. All the way to Jupiter at 5.2 AUs, 0.2 times farther away from the sun than the Earth. And if you wanted to figure out distance, just multiply that number by 93 million miles, or 150 million kilometers. Saturn, 9.5 AUs, almost twice as far out from Jupiter. Uranus, sorry, we've got comets down here. This is actually a very famous comet. This is Halley's Comet, which gets 0.8, which makes it a little farther away from the sun than the Earth on its closest perihelion. And it goes all the way out to 35, which is going to kick it way the heck out here at its aphelion. It's an incredibly elliptical orbit, so it comes in like this, and it takes 72 years to do this trip, where we take 1 year to go around us. For us to go around the sun, Jupiter takes about 12 years, Pluto takes 230 years. Uranus out there at 9.2, Neptune at about 30. One of the problems with Pluto is it actually crosses the orbit of Neptune. It goes from 30 out to about 39 AUs. We have Makemake, which is another minor planet at 45.3, and you can see we're going way the heck out there. We have the Kuiper Belt, 40 to 48 AUs, so almost 10 AUs wide. And then we have Eris way out there at about 100 AUs. So 100 times farther away from the sun, and that would make the sun very, very, very small, probably not even a bright star, although it is gravitationally locked to our sun, just like we are. Okay, and again, I would like you to write those numbers down with the names all the way out to the edge of the paper. Again, not to scale. Here's our near space. We're actually looking at, and I can't really figure out how far this is, but this is looking at the middle of the Milky Way galaxy. We're located out here looking toward the center. We have M31, we have the Andromeda galaxy out there, we have clusters of lots of things, but if we're taking a look at this, the colors are actually represented by the redshift, and where the numbers that you see by these things are actually showing you how far away they're receding, or in this case coming toward us. So looks like most everything out there is moving farther away from us. Okay, let's make a circle that is 12.5 light years in radius. So there's 10 light years, and you can see we have our closest neighboring star, Proxima Centauri, or Alpha Centauri. You can see some other stars, and these are all relatively, I can't say all of them, but they're relatively dim stars. If they were as bright or as big as some of the other stars that are out there, Procyon is actually a pretty good sized star. Sirius is the biggest star we can see in our sky other than the sun. But so those are actually two fairly good sized ones, but the rest of these are all relatively small and tough to see. In fact, a lot of these, like Centaurus and the Bernard star, I think are actually only visible if you're closer to the equator in the northern hemisphere or in the southern hemisphere. Okay, here's 250 light years in radius, so 500 light years across. And now we're actually getting Ursa Major constellation. There's actually minor, and we're seeing other things. Galactic center is still not in our view, but it's in this direction, so more stars this way than there are in other directions, but you see lots of neighboring stars within that 250 light year barrier. And what that basically means is anything on the outside of the circle, let's say that star's on the circle, and you can see it with your eyes, the light that actually hits the Earth traveled 250 years to get to you at the speed of light, 186,000 miles per second. If we go out 5,000 light years in radius, we start seeing one of the biggest, brightest stars we can see with our eyes. There's another one right there. This is Orion, Orion's belt. This one's actually in Cygnus the Swan. And then we see some other constellations that are showing up. The galactic center, again, is in this direction toward these smaller bands. Go out 5 or 50,000 light years, and we start actually seeing the inside, because we're about 100,000 light years across, so 50,000 in each direction. If you take a look, where are we? Sun's location's about 2/3 of the way out in this direction. We have the one of the Magellanic Clouds, the Sagittarius dwarf galaxy that's located down here. Some other globular clusters that are outside the Milky Way galaxy. There are some that are actually inside the Milky Way galaxy, but we have this spinning galaxy about 50,000 light years across, 100,000 light years from side to side. Then we go to 500,000 light years. Now we have the Milky Way inside. We have the large Magellanic Cloud, the small Magellanic Cloud. We have some dwarf galaxies located out there. Go out to 5 million light years, and we actually start seeing some different things. There's Andromeda 1, 2, and 3. And then we see some other things that are located out there as well. Go out 50 million light year radius, and you can start seeing many other things. And as we get farther out, that's 100 million, 500 million, in each 100 million, which is 100,000, 100 million, 1,000 million, so that's a billion. It's times 9. I should have just saw that. I'd like you to know that 3 is 1,000, 6 is a million, 10 is a billion. We're going to start talking about the numbers. And again, these are light years. So this is 100 million light years to travel from that point to that point. And then this is basically the known area that we can see with even some of the biggest telescopes. That's a billion light years across. This is 1.4 times 10 to the 10th, so 10 billion light years across, and basically is the known universe. Origin and fate of the universe. This part of astronomy is called cosmology. Cosmology seeks to understand and to explain the universe, and from where it began to everything that happens to where we think it might end, or it could even go on forever. Here are a couple of pictures. We're located about right here right now, and if you take a look at the present, all 3 of these models actually have the universe as being about the same size. We have one that's called the Big Rip. This is what's called the Big Chill. We have Einstein's theory where it continues forever. And then we have what's called the Big Crunch, where we have a Big Bang, and then sometime in the future it comes back together, and then there's another Big Bang, and then it comes back together. And this is if we have enough gravity. This is if we have less gravity than what we think now, and this is if we have the same amount of gravity as we have. And again, I would like you to draw this. But basically what happens is we have the Big Bang, we have 10 billion years ago, and we have some of these supernovas, and what we're doing is we're looking at the supernovas to actually make some observations on how they're reacting to their environment, and that may give us an understanding. Even we won't have to wait and actually see. We may give us an understanding of which one of these 3 routes we're going to take, whether we expand forever, whether we come back together, or whether we expand forever but we don't rip apart like we do in the Big Chill. Beginning to the end. Dawn of time. We're not sure what happened back then, but we think it expanded. We'll talk about the ideas that we used to show that it had expanded, and it's pretty much undeniable. But a tiny fraction later, we actually started getting subatomic particles. Then we have the inflation period, and that has continued to 3.7 billion years later, where we have the known universe. Here's a large-scale timing. I'm not sure if you can see this section back there, but we have a Big Bang, and then we even have like tenths, hundredths, 1,000th of a second later. We actually have WIPs form, and I'll show you WIPs, I think, in this section. Then we have neutrons and protons, and then we have nuclei forming, and they combine to make atoms. That's 300,000, and this is where we actually start getting what's called the dark ages. And they begin, and then we have the first stars that form, and then we have the first galaxies that form, and this is actually where the dark ages end, because we start getting late in the universe. And then 3 billion years later, we have reheating of the intergalactic gases, and then we have cluster galaxies forming, and then we have the clusters of galaxies form, and this is where we are at 3.7 billion years, where we are today. We have epochs, and I would like you to write these. We have the Big Bang, which starts the time. We have the radiation era, where we actually started producing some radiation, but it wasn't really light. It was more energy and gravity and time. And then 300,000, we have the Dark Ages beginning, where we don't really have stars forming. 3 million years, 300 million years ago, we actually started getting stars, and we started getting nascent galaxies, which are the star galaxies forming. About 1 billion years, we have the Dark Ages end. 4.5 billion years, we throw in the sun, the earth, and our solar system. And then 13.7 billion years we have today. And we can see all of this looking back through time with Hubble. We just have not made it past into this area because we can't see it. Here's a picture that I've shown from Earth science as long as I can remember. Time beginning, and if you take a look, the temperature 10 times 20 to 27 degrees Celsius, that's really, really, really hot. In fact, it's so hot that things can't come together. Then we start getting stuff coming together. We got quarks, they clump into the protons and neutrons, and then it's still too hot to form atoms. 3 minutes later, but you can see it's cooled quite a bit in 3 minutes. From 300,000 years, it's 10,000 degrees Celsius. We get electrons, and those electrons actually bond with protons and neutrons to form atoms, and then we start getting stars and proto-galaxies 1 billion years when it's cooled down to 200 degrees below zero, and right now we're 3 degrees above Kelvin for the entire universe altogether. Remember, we have a lot of interstellar, intergalactic space. No stars, no real heat, so we have some really cold areas, but we do have some really warm areas too with the stars and the galaxies. Average it all together, 3 degrees warmer than 0 Kelvin. And then our last slide, hundreds of billion years from now, the universe may appear frozen. As we look into space, the only light we'll actually see is maybe the galaxies that are close to us, which are called the local group. That's if we're around to actually see it. And that is the end of this section, and thank you again for stopping by.